Node.js ships with a built-in module for x-axis scaling, cluster. It's available without installing any packages, and it implements a master worker architecture that lets multiple Node.js processes share the same TCP port. Here's how it works. You run your server script, and it checks, am I the master process or a worker process? The master's job is to fork worker processes, one per CPU core is the standard approach, and monitor them for crashes. The worker's job is to run your actual HTTP server and handle requests. The remarkable thing is that all workers bind to the same port number. You don't need 8 different port numbers for 8 workers. The operating system and cluster module coordinate to route incoming connections to available workers. The default load balancing strategy on Linux is round robin. Connection 1 goes to worker 1, connection 2 to worker 2, connection 3 to worker 3, and so on cyclically. This distributes load reasonably evenly across workers. On Windows, the strategy is different. The OS itself handles load balancing, which may be less evenly distributed. The cluster module also gives you resilience out of the box. When a worker crashes, due to an unhandled exception, out-of-memory error, or any other reason, the master process detects the exit event and can spawn a replacement worker. Your application continues serving traffic even as individual workers crash and restart. For a typical Node.js HTTP server, switching from a single process to a cluster is fewer than 10 lines of code change. The application code itself doesn't change at all, only the startup code changes to add the master worker logic. This is the most impactful improvement per line of code you can make to most Node.js applications. Here's a production scenario that separates experienced Node.js operators from beginners. You need to deploy a new version of your application, but you can't afford downtime. Your service is processing payments, real-time bids, or live chat messages. Taking the server down for even 30 seconds is unacceptable. The naive approach is to kill all workers and restart them with the new code simultaneously. During the restart window, no workers are available. Requests either fail or queue up. This is downtime, brief, but real. The zero-downtime restart strategy is elegant: kill workers one at a time. Keep all the others running. Here's the sequence: send a signal to worker 1. Worker 1 finishes its current requests, then exits gracefully. The master detects the exit, starts a new worker with the updated code. New worker 1 starts accepting requests. Now send the signal to worker 2. Repeat until all workers have been cycled. At no point during this process is the server unavailable. Old workers are handling requests while new workers spin up. The transition is invisible to users. Implementing this requires worker processes to handle the shutdown signal gracefully, stop accepting new connections, wait for in-flight requests to complete, then exit. Node.js HTTP servers support this through server.close, which stops accepting new connections while allowing existing ones to finish. The pattern has a name: graceful shutdown. It's not just for zero-downtime deploys, it's also essential for clean pod termination in Kubernetes. When Kubernetes needs to kill a pod, it sends sigterm. A well-behaved Node.js application catches sigterm, calls server.close, waits for in-flight requests, and exits cleanly. Kubernetes waits up to a configurable timeout before force-killing the process. Every production Node.js application should implement graceful shutdown. It's a small amount of code that prevents request drops during every deploy. Scaling to multiple processes introduces a problem that surprises many developers: session state. Imagine your application stores session information in memory, a JavaScript map or object that tracks which users are logged in, their shopping carts, their WebSocket connections. With a single process, this works fine. With multiple workers, it breaks. Worker 1 might have stored user Alice's session. User Alice's next request might go to worker 2. Worker 2 has no record of Alice's session. Alice is inexplicably logged out. This is the stateful communication problem, and it's one of the fundamental challenges of horizontal scaling. The simplest workaround is sticky sessions, also called session affinity. The load balancer is configured to always route the same client to the same worker, typically based on a hash of the client's IP address or a cookie value. Alice always goes to worker 2. Problem solved. Except it's not really solved, it's hidden. If worker 2 crashes, Alice loses her session. Load is no longer evenly distributed if some clients have heavier sessions than others. And sticky sessions completely break the resilience story: worker crashes now affect specific users. The proper solution is to externalize state. Move session data out of the Node.js process and into a shared data store that all workers can access. Redis is the canonical choice for session storage. It's fast, supports arbitrary data structures, and can be clustered for high availability. All workers read and write session data to Redis. Any worker can handle any request because the state is not in the worker, it's in Redis. This principle extends beyond sessions. Any state that must survive worker restarts, or be visible across multiple workers, must live outside the process. Redis for sessions and ephemeral state. A database for persistent data. This is the key architectural discipline that makes horizontal scaling actually work. At production scale, you typically add another layer in front of your Node.js cluster, a reverse proxy. Nginx is the most widely deployed reverse proxy for Node.js applications in production. A reverse proxy sits between the internet and your application servers. Clients connect to Nginx. Nginx forwards requests to your Node.js processes. Your Node.js processes never speak directly to the public internet. Why add this layer? Several reasons. Nginx is extremely efficient at terminating SSL/TLS. The cryptographic overhead of HTTPS happens in Nginx, not in your Node.js processes. Nginx can serve static files, images, CSS, JavaScript bundles directly from disk without involving Node.js at all. Nginx handles connection management extremely efficiently with very low memory overhead per connection, which is important when you have many idle connections. Nginx also provides load balancing across multiple server instances, not just multiple processes on one machine, but multiple machines. You configure an upstream block listing all your Node.js server addresses, and Nginx distributes requests across them. Round robin is the default, but you can also use leased connections, IP hash for sticky sessions, or weighted distribution. Health checks are another Nginx feature. Configure Nginx to periodically test each upstream server and remove unhealthy ones from rotation automatically. A Node.js instance that is slow or unresponsive stops receiving traffic without any manual intervention. The full production stack often looks like this. Nginx is the internet-facing layer handling SSL, static files, and load balancing, multiple Node.js cluster instances across multiple machines handling application logic, Redis for shared session and cache state, a primary database with read replicas for data storage. Each layer does what it's best at. This is the architecture that serves millions of requests per day reliably. Let's bring together everything we've covered about cloning and load balancing and be explicit about how these approaches compose in practice. The cluster module is your starting point for using all CPU cores on a single machine. It's built-in, requires minimal code, and gives you both performance and resilience. This should be the default for any Node.js application running in production. Use PM2 as your process manager to get cluster mode plus automatic restarts, log management, and monitoring in one tool. Nginx's reverse proxy is the next layer, enabling you to handle SSL efficiently, serve static assets fast, and distribute load across multiple machines. At this layer, you're scaling beyond a single machine. You've added horizontal scaling at the infrastructure level. The stateful communication challenge is the hidden tax of horizontal scaling. Every time you add another worker or another machine, you must ask, does my application store any state that belongs to a specific process? If yes, that state must be externalized to Redis or a database before scaling will work correctly. Zero-downtime restarts and graceful shutdown are operational practices that should be implemented from day one. They're cheap to add and expensive to retrofit. In Kubernetes environments, they're not optional. Pods are killed and restarted regularly as part of normal operation. There's one more scaling approach the book covers that goes beyond what we've discussed: dynamic horizontal scaling, automatically adding and removing instances based on load, using a service registry to keep track of what's running. That's where containers and orchestration tools like Kubernetes enter the picture. The combination of these scaling fundamentals with container orchestration is what modern cloud-native Node.js applications are built on.